Good morning, 3U and 4C chemistry students, or whatever time it is for you when you're looking at this. I know some of you have been keeping some funny hours. Anyways, today we're going to continue on with pH, and I was hoping that you would have gone through this note yourself with the textbook and got a lot of the information down. If not, just follow along. But what is super important is that when we get to calculations, you have your scientific calculator out and you try to get the answers that are correct, because every brand of calculator is a little bit different. So I can't just say, press this, then press this, then press that, because it won't necessarily work on your calculator. All right, so as a review, pH is the power of hydrogen, which is really just saying the concentration of hydrogen ions. Now, you've also noticed from our last lesson that hydrogen ions can sometimes be called hydronium ions. I need to get a pen here, I just realized. There we go. So H3O plus is hydronium. That's when hydrogen ions combine with water, or just plain old hydrogen ions is another way you can think about it, because either way those concentrations will be the same. Okay, now on the pH scale, every step on that scale represents a 10-fold change in concentration. So it's called a logarithmic scale, and it's to the base 10, and that is why you need a calculator with a log button today. So on this pH scale, if you were using your textbook, for example, you might have added in, some lemon here, or perhaps some over here we've got 1.0 mole per liter sodium hydroxide, and there was a few other examples from your book as well. But you have perhaps made your own pH scale already from our last lesson. All right, so in terms of this, what each step in number represents, if we were to compare tomatoes and vinegar, for example, so tomatoes have a pH of about 4, and every time we do a step, we said it's a change in 10. So this would be 10 times, and this would be 10 times. So if the question was, how much more acidic is vinegar compared to tomato? Oh, excuse me, we have a little contractor working here in the basement, which I think you might be able to hear. So vinegar is 10 times 10 times, which is 100 times more acidic than tomato. Okay, so 100 times more acidic, which is why drinking vinegar would be very painful on your throat, and you eat tomatoes all the time. So similarly, we could look over here at, say, what could we look at? So an indigestion tablet here, and we're going to compare it to drain cleaner. Okay, so every step is 10 times. So to do that, you're going to say 10 times 10 times 10 times 10, which is going to give you an answer with 4 zeros. Okay, or 10,000. So drain cleaner is 10,000 times more basic than, we'll say, Tums. Okay, and that's why it can clean your drain. All right. Now, the calculations that we're going to be doing today are figuring out how you can calculate pH if you know the concentration of hydrogen ions, or going the other way, you can do concentration of hydrogen ions if you know the pH. So this is the formula that you could have copied from the textbook, and there was a little 10 here. So it said negative log 10, and then the hydrogen ion concentration. Oops, I see the little plus sign seems to be gone there. Which again, this could just be H plus. Okay, I've scratched out the 10 because the calculator you guys will be using will definitely be a log of base 10. So the 10 there is kind of confusing because you might think you need to press a 10, but you do not. It's incorporated. So just think of this calculation as if you're calculating pH, you need to do the negative log of your hydrogen ion concentration. All right, so water is neutral, which you should remember from grade 10, which is really saying that the hydrogen ion or hydronium and the hydroxide, OH, are completely equal, and they both happen to equal 1.0 times 10 to the negative 7 moles per liter. And if you want to expand that out, that's what that would look like. So a very, very, very low concentration of each ion in neutral water. So you should try this on your calculator now. See if you can somehow do a log of that number and get an answer of 7. Now, this is a hint I do all the time. I ignore the negative sign. I don't put that in when I'm doing my calculation. I take the log of this number, and then my answer will come out to be negative 7, but there's no such thing as a negative value on the pH scale. So you just have to realize, oh yeah, I forgot about the negative, or I left the negative out, so I'm going to now multiply that through, and that will turn it into a positive 7. Now, another hint, if you're having trouble putting in 1 times 10 to the exponent negative 7, try just putting it in like this, like just expand it out. So you're going to have, if this was originally 1, you're going to have to move the decimal 7 places backwards, which is going to give you this. So if that was 1.0, 1, 2, 3, 4, 5, 6, 7. So if you just do that, all you now have to do is do the log button and that number and press equals, and you should be good. Okay. All right, now I'm not going to be picky about significant digits in any way in grade 11, but just for the record, and I will try to do my questions to show you this, usually it is a funny rule that pH will have the same number of decimal places as you have in significant digits in your concentration. So if your concentration has 2 significant digits, as all of my examples do here, 1.0, 1.0, 9.5, 4.3, so 2 sig digs. So all of my final answers for pH have 2 decimal places. But you know what? If you have rounded yours off, it's not a big deal. I'm not going to be picky. And some people's calculators actually won't be able to express the answer as accurately as others because some people can have 8 digits on their screen, some people have 9, etc. So you might find occasionally that your answer just is a little more rounded and there's nothing you can do about it. So that is fine. Okay, so these were your practice questions to get, figure out if you can get along with your calculator and get the right answers. So the first one I had done for you. So again, if you take the log of this tiny number, you should just get 6. Now, when you just have 1.0 times 10 to like a full number, like a whole number, I guess I should say, nothing with a decimal in your main number, not your exponent, then you actually don't even need your calculator. So for those two, you could actually do them without a calculator. Oops, I should be able to spell here. No calculator needed. Okay, because if you know the exponent and it's just 1, just a whole number of 1, then that exponent is actually going to be your pH. Okay, so 6 is below 7, so we know it's an acid, and 11 is above 7, so we know that is a base. Now these ones you do have to put in your calculator. There's no easy way around this. So again, you could expand that number out if needed, if that helps, and you should get 10.02, which is a base. And this one you have to use your calculator. There's no really work for me to show you here because again, how you put it into your calculator is very unique to your calculator. So play with them until you can get it to spit out those numbers. Okay, and remember, if you just If you leave the negative out of your work, you'll at first have negative 10.02 and then just make it a positive. Okay, so going backwards from that, we can figure out your hydrogen ion or your hydronium ion concentration by doing 10 to the exponent of the negative pH. Now this little negative cannot be ignored. You absolutely have to put it in there. So you'll notice on your calculator that this button looks like 10 to the x that you're going to want to use, and it should be the second function of the log button that you were using in the last calculation. So you'll have to use your second function button to make this work. Okay, so similarly, first two examples, you actually didn't need a calculator. So a pH of 8, your hydrogen ion or hydronium ion concentration is just 10 to the negative 8, or 1 times 10 to the negative 8. So the 8 is your exponent, and because it's just 1 times that, you could expand it if you want, but you can get that without a calculator. Okay, so same with, my first practice was A. So it's just 1 times 10 to the negative 5 if the pH is 5. Now these two you need to practice. So the hydrogen ion will be 10 to the exponent negative 8.43. And remember, you need to use the second function of your log button. So, and please be sure to put the negative in. You should have a little button on your calculator that kind of says plus minus that you can use to make something negative as opposed to literally your subtract button. So you'll probably get something around 3.7 times 10 to the negative 9, depending on your calculator. Some of you might just get 4 times 10 to the negative 9. Some people might get, I'm trying to think here, just 3 even. It might have just chopped it off. So you may have got 3 times 10 to the negative 9 or 4 times 10 to the negative 9. Either way, that's acceptable just because you have no control over that. Okay, this would be the best answer, 3.7, because of the fact that our pH had 2 decimal places. So I actually have 2 significant digits here. Okay, and then C, practice that as well to see if you can get 9.8 times 10 to the negative 13. And my units are missing there, moles per liter. Okay, so now we can calculate pH and we can calculate hydrogen ion concentration. Now, another important relationship in neutral water, we said the hydrogen ion and hydroxide are equal. So we can use that to come up with a formula because they both equaled 1 times 10 to the negative 7. So based on that, if you were to multiply 1 times 10 to the negative 7 times 1 times 10 to the negative 7, you would get 1 times 10 to the negative 14. And that is a relationship that we can use to now see how the hydroxide ion concentration and the hydrogen ion concentration compare to each other. And how pH and something called pOH compare. So this is a chart you could copy from your textbook, but I just want you to notice a couple things. Anytime you have 10 to the 0, it's just like saying 1. So this would be saying the concentration is 1 mole per liter of hydrogen. That is a high concentration. That's going to result in a very low pH of 0, so very, very, very acidic. And the hydroxide is going to be tiny, tiny, tiny. It's 10 to the negative 14. So if this number is big, this number is tiny. And then as you work your way down, you'll see that this number gets tiny for hydrogen, but the hydroxide gets huge. Okay. Now, pH and pOH, as we know, the pH scale goes from 0 to 14, or sometimes we say 1 to 14, but really it's 0. pOH is just another way you can express the acidity or basicity of a substance. And it's completely opposite because if you'll notice, there's a relationship here where they always add up to 14. Okay, so if you know one, you can figure out the other. So 0 plus 14, 1 plus 13, 2 plus 12, 3 plus 11, etc. Okay, so we have an identical formula for calculating pOH, and we're going to do the negative log of the hydroxide ion concentration. Again, there would be a base 10 there, but don't worry about it. And then we said if you know either of those, you can use this idea that the two of them are going to add up to be 14. So if the pH is 5, what does the pOH equal? So we have 5 plus pOH equals 14. You can subtract that off the other side, and pOH is 9. Okay. Now your textbook didn't cover this final formula, which I don't know why it didn't, but we have the opposite formula to our hydrogen ion concentration, where we can get hydroxide ion concentration by doing 10 to the negative pOH. And again, that's that same button. Okay, so this is a little bit of review from yesterday. So indicators change color depending on the pH, and some indicators only are one color or another color. So we usually just call those indicators. So phenolphthalein, bromothiamyl blue are very common ones that we would have used in the lab. And on the back of your periodic table, you can see a range. There's a chart on the back. It's at the bottom right. And it shows all sorts of different indicators and the range at which they change color. So somewhere between 8.2 and 10, phenolphthalein will change from clear on the 8.2 and below side, whereas somewhere in that range, it's going to turn to pink. So the more basic something is, the pinker it will be. And then here's another common one that changes somewhere between 6 and 7.6. So on this side, here, bromothiamyl blue is yellow, and on this side it's blue. So it can help you identify if it's an acid or base. Now, universal indicators change a whole bunch of different colors, and therefore you can kind of guess at the pH better. Okay, so the practice questions I gave you, I do want to go through and do a couple. The first one here in blue, technically, you did not need your calculator to do that, okay, because of the fact that I gave you the hydrogen ion concentration and it was a whole number, 1 times 10 to the negative 3. So as a result, you know that the pH has to be 3, but you can do it in your calculator. Okay, so that's the first thing I did. So I put number 1 here to say I figured out pH. There's the calculation. Then I'm going to do the easiest calculation. Once I know pH, I'm going to get the pOH by knowing that 3 plus 11 has got to equal 14, so pOH has to be 11. So that's the second calculation. And once I know the pOH, I can do my third using this formula. So here's our 6 formulas that we've now gone over. You'll use the first 5 a lot. I rarely use this one, because you just don't have to, but it's there if you want to. So 1 times 10 to the negative 11. All right, so I thought we'd do the middle one together. Okay, and of course, to figure out that it's an acid, you look at the pH is probably the easiest, and if it's under 7, it's going to be an acid. Okay, so for number 2, the information they've given us is the hydroxide ion concentration. So the first thing I'm going to do is figure out the pOH. So that's going to be my first thing. Okay, so pOH equals negative log of hydroxide ion. And remember, I'm not going to put the negative in my calculator for this. So 6.5 times 10 to the negative 5. And I have 2 sig digs, so ideally I'm going to keep 2 decimal places on my pOH. Okay, so 4.19. So now I'm going to do the easy one. I'm going to get the pH. Okay, so 14 subtract 4.19 is 9.81, and that is my pH. I have POH. Okay, so at this point, if you want, you could go over here and figure out whether we have an acid or base, and we're above 7, so we definitely have a base. Okay. And then the third calculation I'm going to do is figure out my hydrogen ion concentration. And so that is going to be hydrogen or hydronium is 10 to the negative pH, which is going to be 10 to the negative 9.81, which you have to figure out how your calculator is going to work. And you get 1.55 times 10 to the negative 10, sorry, to the negative 10. And we are having 2 decimal places here, so I'm going to just round this to 2 significant digits, so 1.6 times 10 to the negative 10 moles per liter. Okay, so if you are given any single piece of information of these 4 entities, you can figure out the other 3. And the order that I've done them, makes sense to me, but it's not the be-all, end-all. You don't have to necessarily do it in that order. Now, in the third example, just to mix it up a little bit, I did use this formula here to get my hydroxide, but I didn't have to. I totally could have done the formula where we do 10 to the negative POH, so I could have done 10 to the negative 10.6, and I would have got the same answer, which is what, 2.5 times 10 to the negative 11 moles per liter. Okay. All right. So I'm going to do 2 more questions. So on page 271, there is a question that asks you to determine the pH. So keep straight what you're going for. Always write down what you're trying to solve with a question mark, and then write down what you know. And what they give you is the hydroxide ion concentration. So a lot of this is about just careful reading to make sure you don't assume that you can just use one formula and get the right answer. So if we have hydroxide ion concentration, we can totally figure out POH by doing a negative log of that concentration. And that should come out to 1.92. That's the POH though. So therefore the pH is going to be 14 minus 1.92, which is 12.08. So give yourself a pat in the back if you tried that and got that one right. Okay, so then there's also a practice problem on page 272. And on this question, they ask for 2 pieces of information. They want to know the POH, and they also want to know the concentration of the original solution, which is potassium hydroxide. Okay, and what they've given is the pH. So pH is 11.14. So the first one is the easiest to do, where we're going to get the POH. And it's going to be 14 subtract 11.14, which will be 2.86. Okay, so there's one question answered. That's POH. Now, once we know the POH, we can figure out the hydroxide concentration, which is not what the question's asking for, but it'll get us very close. And then we'll just have one extra little step. So hydroxide ion concentration is going to be 10 to the negative POH, 10 to the negative 2.86, which equals 1.4 times 10 to the negative 3 moles per liter. And that is hydroxide ion concentration. So we can do a little ratio here that basically says for every 1 piece of potassium hydroxide I have 1 hydroxide ion based on the formula. Because some bases might have 2, like calcium hydroxide is Ca bracket OH bracket 2. But this is a 1-to-1 ratio. So therefore, hydroxide is going to cancel, and I do have 1.4 times 10 to the negative 3 mole per liter KOH solution. Okay, that is it, and you're going to practice a few textbook questions with those types of calculations, and good luck.